Thank you, everyone. Thanks for coming to my talk. Today I'm going to be talking about container networking using Netkit. So just really quickly, a little bit about me. My name is Mike. I'm a software engineer at Meta. I work on the containers team. I live in Brooklyn, New York City. There's just a photo of my weekend hobby. I like to do rally racing, so happy to talk about that as well. But today I'm here to talk about the Netkit device. So I'm going to quickly go over, kind of introducing container networking, talk about how the Netkit device came to be. Then I want to talk a little bit about how we implemented Netkit at Meta, kind of some of the issues we ran into as we rolled it out, and some of the benefits that we saw. And then at the end, I'll try to leave some time for questions. Just kind of introduce container networking in general. So at Meta, we have obviously a lot of network traffic coming into our data centers. And if you look at a typical data center, you would see rows and rows of machines like this. On each machine, we have, of course, a desire to run many jobs at the same time. So this is kind of logically how it might look. So there's a network switch at the top, and it's connected to multiple hosts in a single rack. And on each of those hosts, we use containers to run multiple services on the same system. So a typical host might have, sometimes multiple, even thousands of services running at the same time. And of course, we want to be able to isolate the networking between these services. So before we had network namespaces, we would have this issue. If there's two containers running on the same host and they both want to use a similar IP address and port, there would be a conflict. They're all kind of sharing the same network environment. This has kind of practical implications. All of these services would have to coordinate their networking setup. But of course, there's also security implications there. Service could come and snoop on another service's network traffic, things like that. So network namespaces was introduced kind of to solve this problem and introduce additional layer of security into the networking. So with network namespaces, once you put a service into a network namespace, it has basically its own view of the network. You could almost think of it as if it's running on a completely separate machine on a different network. So here we see that this problem with trying to bind to the same port, this is solved because each service on this machine has its own list of ports, its own interfaces, and it can now bind to that same port. So service A, in this case, it's not aware of service B at all, and the networking can cooperate together. They don't need to kind of talk to each other at all. And the way this is set up initially was using these virtual Ethernet devices. So when you create a network namespace, you would create, in this case, the virtual Ethernet A device and connect it to another virtual Ethernet device inside network namespace A. And you would create virtual Ethernet B device and connect it to the network namespace B. And this would kind of act similar to if there's virtual Ethernet cable wired from the network namespace to the host namespace. So this works for security, but it turns out it introduces a performance impact. And the reason is that every time you transmit now a packet from the container to the outside world, it has to essentially get transmitted twice. So in the beginning, it gets transmitted from the virtual Ethernet device inside the container to the one outside in the host, and then it gets transmitted again from the host network adapter out to the outside world. So what's happening here is essentially there's a lot of extra activity going on the CPU. It has to handle these additional IRQ interrupts. So the Netkit device was introduced essentially to solve this problem. And the way it works with Netkit is when you create the first adapter on the host side, it actually creates two devices. There's what they call a primary and a peer. So the primary exists in the host network namespace, and the peer can then be moved inside the task network namespace. And this allows the traffic inside the container to immediately be available in the host network namespace, And if you have BPF programs that you want to filter the traffic, they can run it, like essentially they're running inside the container, but the packets are able to be processed immediately. So in like practical terms, what this means is with VETH, you can see on the far left here, if we use kind of an imaginary 100 megabit adapter, with VETH, we were only able to get about like 60 megabits per second out of that adapter. So essentially, it's about 60% of the performance of the host kind of baseline performance. And we see here, using like Netkit and BPF programs, we can get the full performance. So we get the equal to the host performance. So that's kind of the headline here, is that once we enable Netkit, we can use network namespaces now. We get that isolation between the tasks, but without any performance implications. So that's kind of a summary of kind of why we wanted to use Netkit and how it works. So I'd like to just quickly describe how we rolled it out at Meta, like what went into implementing this. Quickly, how we work on containers at Meta, we have this service called the Twine scheduler. So whenever a user requests to start a service, the request goes to this scheduler program, which is kind of a back-end service that will assign that job to a particular machine. The scheduler sends a request down to our Twine agent, which will create the container for the job and do all of this networking setup. So this is where we implemented the Netkit device. So every time a job starts up, it automatically creates these adapters and then does the networking configuration for them. And this agent is responsible for the resource control for these jobs, like assigning how much memory and how much CPU they're able to use. Of course, like creating the actual container and setting up the isolation between the jobs so these services don't kind of step on each other's toes. So in terms of where we're at with the rollout status today, about 66% of all of the containers that we create are containers with root or without root. Either case, it should work. Yeah, I guess kind of to follow up on some of the previous questions too, the way that this appears, the way that this appears to this task is the same as kind of any other network adapter. And in fact, inside the container, if you enter the container, it looks like ETH0 in the container, and there was like no changes that the tasks need to make. They can just send like normal network traffic, and then under the hood, it's implemented as this Netkit device. But to the container, it just looks like a normal network device, so they don't have to kind of do any special setup. The setup is all done from the host side, and then inside the container, it just is like a normal networking setup. All right, so yeah, so let me finish the slides quickly, then we can do more questions. So yeah, as I was saying, the network namespace at this point, we have enabled about 66%. The way that we roll this out is via a feature flag. So as I mentioned, like there's kind of no work for the tasks to do. We turn this on in the back end, and next time they restart their task, they will just start using Netkit. We have it rolled out based on the criticality of the job. So when we say 66% of the tasks, we started with like the less critical tasks. So every service owner at Meta will specify the criticality of their service. If it's a tier 0, this would represent like if the service goes down, the whole website goes down, and it goes all the way down 1, 2, 3, 4. So we started with the less critical ones, and we're working our way up. And as we get to the end here, you can see it kind of slows down. We want to be more careful with these like final highly critical jobs. But yeah, importantly, like this is fully transparent to the service owners. They don't need to do any special work here. Once we turn it on for their job, it just starts using this new device, and they get the performance benefits. So just to go through like a real-world example here, this is one team that was trying to enable what we call like stacking of their jobs. So what that means is instead of like one single large task that takes up an entire machine, they can run 4 copies of their task at the same time. It's better for the service owner. They don't really need to specify any of the particulars of the hardware. It's also better for our operations in that sense. There's no specific hardware requirements that we have. We can kind of move the jobs around more easily. But what we were finding was when they tried to do this stacking, their latency was just going way up. So in the beginning here, without Netkit, the latency was going up to around 12 seconds. And once we turned on Netkit, that latency immediately dropped to around 100 milliseconds. So this was really kind of an extreme example, but it does show how that soft IRQ usage that I mentioned before, it can really kind of add up and start to affect these tasks if they are really heavily using the CPU and if they're affected by this performance. So it's not every single task that is going to have this heavy network usage, but for tasks that do have a performance dependency, it really does make a big difference. So I wanted to kind of quickly go through some of the next things that the team's working on at the moment for this. So one of them is called IP router system. So I mentioned the ability to attach BPF programs in the container to do traffic filtering. Today, the way we have it set up, each container will get its own new BPF program. So if we have 1,000 tasks on a host, there would be 1,000 BPF programs kind of in a chain. And this starts to eventually affect latency as well, because in the worst case, the traffic that we're trying to send has to go through each one of those BPF programs. So at the moment, we're working on this IP router system, which would replace all of that with a single BPF program that just has the map of all of the containers on the system, and it just knows where to route that traffic. Another thing that we're working on is NUMA-aware networking. So when we have these containers running on the host, for performance reasons, it's very beneficial if we can keep all of the networking in the same NUMA node. And this is very important as we have GPU hosts where the system is kind of divided up into these NUMA nodes, and anytime you have to copy any kind of data outside of the NUMA node, there's a big performance impact. So we're working on making sure the container is aligned within the same NUMA node all the way kind of end to end. And the final one I wanted to mention is the next step for Netkit would be to use it also with VMs. So not just a container, but if there's a VM running on a machine, we could have the same kind of performance benefits using this system called AFXDP. Essentially what this does is create the shared address space inside the VM and the host, and then similarly, any traffic being sent out of the VM will immediately be available in the host. So we can take the same kind of performance that we've applied to containers and then apply it also to VMs. So in closing, I just wanted to mention quickly that there was a lot of open source community support here. We couldn't have done this without all of the authors, the developers working at different companies who helped to write this code. At Meta, I wanted to mention Takshak, Raman, and Martin, who really helped with implementing this and working out some of the bugs. And at Isovalent in particular, there's a lot of really helpful blog posts out there, other talks that were given, Daniel Borgman, Nicolay, Nico, and Bill Mulligan. They've really put a lot of helpful, useful information out there. And then finally, I know there's a few questions about the particulars of how this works. So if you're interested to learn more, I've put up some demos and some additional links to other resources up here at that link. And yeah, that was all I had. So I wonder if there's any questions. Good.
Yeah, so a lot of people use nspawn for launching containers. What is the status of integrating Netkit into nspawn so we get that instead of v's from now on?
Yeah, that's a great question. So that's actually a task that we have in our backlog, which we're hoping to get somebody to work on probably in the beginning of next year to add this into systemd networkd. So it would be available as another device type flag that you could add into the systemd networkd setup. And then yeah, so at the link here, there's kind of like the step-by-step walkthrough. So once you create the container, as of today, you could create the devices using just like IP link add, those type of commands. But eventually, we'd like to have this like support in like systemd networkd. Yes, one here.
You kept mentioning BPF programs, but you did not explain how frames are moved from the external Netkit device to the actual network interface. Is this the purpose of the BPF programs? Are they provided by your orchestrator, by the driver? How does this part work?
Yeah, so the question was around like how do the BPF programs actually manage moving the data between the network namespaces? The reason that this works is essentially it's a single driver code, and then in the driver code in the setup, it's creating two devices, and those two devices have access to the same memory under the hood. So with VEs, there's actually like you have to create both separate devices, and then the only way that they can communicate with each other is by sending like network traffic. But with Netkit, those BPF programs can access the data kind of instantly in the host namespace, since it's just a single device that just has like two ends basically. Does that make sense?
We'll talk about later.
Can Netkit be used with SRIOV, or is there any relation between SRIOV and Netkit?
I'm not that familiar with that.
The ability to like defer the virtualization on the network card.
I think it should be compatible. I'm not sure that there's any I don't know of any reason that it wouldn't work that way. It kind of should just work like any other network adapter, but yeah, I'm not too sure.
Thanks.
Are there any downsides with this approach compared to traditional VHD?
Yeah, that's a good question. So I would say so far the only real downside that we've seen is around like debugging. So one of the nice things about VETH is like because it just works like any other network card on the network, all of the normal networking stack, kind of applies. So debugging, like if there's a network connectivity issue, it works just like any other, like debugging on any other machine. Once you introduce Netkit, because it's kind of creating this like short circuit from the container to the host, like you kind of have to be aware of that that extra link that's in there. So I'd say the only real downside that we've seen so far, where like teams have asked us to go back to VEs, is if they're like trying to debug some particular network issue, and they just want to go back to VEs, which is like a more familiar solution, and they can kind of get additional debugging output that way.
So it seems that the operation model for VEth and Netkit is roughly the same. So the service owner shouldn't really be able to tell the difference, except he has the better performance. So why there was a reason for Netkit in the first place? Wasn't it possible to change the VEth or add like an additional mode to VEth or something like that, so anyone can reap the benefits without changing anything really? I mean, who is using VEth today?
Yeah, I'm not too sure the technical reasons, like why this couldn't be done kind of as an upgrade. I think the main reason is like with VEth, you generally have to like create two devices, and then like move the second one into the container network namespace. Netkit, it's kind of a different, like from the container creation standpoint, it's a little different because you just create a single device. It automatically creates the peer device which you move. So I think it's like in the driver code setup, it's doing that like creation of the second device. I'm not sure why it was decided, to be done that way. I assume it's because they wanted it to be like a specific choice that the like container creator is choosing to make this Netkit pair, and that allows existing VEth use cases to keep working the same way.
So where does eBPF come in the game there? Do you absolutely need to add eBPF programs to the containers to make this networking at all, or is it just enabling this as an additional filtering features and you don't actually need them?
Yeah, so technically you don't absolutely need the BPF programs to be there to work. You could use it just like any other network adapter, but I think the BPF that it's kind of an additional like hook point that they have added for the Netkit device, which allows it to work much faster. It kind of like hooks the packets at an earlier spot in the transmitting process, and so in the best case scenario. If you detect in the BPF program that a packet is going off of the host, you can just immediately redirect that packet to the host Ethernet adapter, and there's no additional processing that needs to be done. It just immediately gets transmitted out. So like that's like the best case performance scenario. That being said, like for other cases that the BPF program doesn't handle the traffic, like there still is a performance benefit. But I think, yeah, like to get the absolute best performance, it's like the combination of the Netkit with the BPF programs, like picking up the traffic earlier.
Any more questions? One last question? No? Okay, well, thank you very much, Mike, again.
Cool, thank you.